Hello. Thank you to the meeting organizers for this opportunity to present our work and to you for attending our poster. My name is Nathan Meyers and I'm a scientist at GSK. The title of our poster is CDK8 and CDK19 are potential host factors for HBV, but their essential cellular functions pose a therapeutic challenge. Chronic hepatitis B is a significant global health burden with over 240 million infected individuals worldwide. The path to functional cure necessitates discovery of novel therapeutics. To that end, we conducted an HBV phenotypic screen in primary human hepatocytes. We tested over 200,000 compounds for their ability to inhibit HBV and reduce S antigen. A lead hit emerged from this screen and it was further characterized using affinity enrichment chemoproteomics for target identification. This analysis revealed that the lead hit binds several cyclin-dependent kinases, or CDKs, including CDKs 8, 9, and 19, along with their cofactors. These CDKs are involved in RNA transcription. CDKs 8 and 19 are paralogs that associate with the mediator complex to trigger transcription initiation. CDK9 controls release of the RNA polymerase II enzyme from a paused phase into productive elongation. Our hypothesis was that inhibition of these three CDKs could suppress HBV replication and downstream antigen production. To interrogate this hypothesis, we pursued genetic and chemical validation of the individual CDKs to determine which was the most tractable host factor for HBV. We use primary human hepatocytes as the most physiologically relevant in vitro model. For genetic validation, pictured on top, we knocked down targets with shRNA for several days, followed by HBV infection. For chemical validation, shown below, we infected hepatocytes for 7 days before repeat dosing with CDK inhibitors. Looking first at CDK9, you'll see in the plot on the left that we were able to knock down CDK9 at increasing levels. Greater knockdown on the x-axis correlated with higher inhibition of HBV RNA in black and S antigen in blue on the y-axis. However, this reduction was mirrored by a reduction in albumin, shown in green, suggesting a tox-related effect. When we screened inhibitors for CDK9, shown in the plots on the right, we saw a similar profile where HBV RNA and S antigen were reduced in step with albumin. We concluded that there was insufficient therapeutic window to pursue CDK9 as an HBV target. Turning our attention to CDKs 8 and 19, knockdown of these targets proved challenging. I don't show that here, but have data in the poster. We focused our efforts on screening inhibitors, most of which bind both paralogs. Using internal compounds, such as compound C on the left, or compounds from the literature, such as the compound on the right, we found that CDK8/19 inhibitors reduce HBV RNA and S antigen, but the effect was mild, with 60% max inhibition and a shallow hill slope. As we probed this finding, we discovered the effect of CDK8/19 inhibitors is donor-dependent. In some donors, such as donor 1 on the left, the antiviral effect is mild, in black, with minimal tox, in green. In other donors, such as donor 2 on the right, a more pronounced antiviral effect is mirrored by significantly more toxicity. We discovered a feedback loop that drives this effect. When hepatocytes are repeatedly dosed with inhibitors, the cells upregulate CDK8 and CDK19, shown here at the RNA level. Notably, upregulation is stronger in donor 1 where the antiviral effect was milder. Altogether, these data indicate that CDK8 and CDK19 play important roles in HBV replication, but are too essential to hepatocytes to make good therapeutic targets. Thank you for listening, and I'm happy to entertain questions virtually or at my poster.